When we model two variables together, another concept that is important is a concept of independence. And a simple mathematical definition of independence, we say that two random variables x and y are independent if conditional probability of y given x is just equal to the probability of y. It means that knowing anything about x doesn't tell us anything about y. And here's example: if you toss a coin twice, then probability of getting head in the second toss, given that we saw a tail in the first toss, is 1/2. It doesn't really matter what was the outcome of the first toss; it's still 1/2 chance of seeing the head in the second toss. So one coin toss is completely independent of another coin toss. And another rule that allows us to calculate conditional probabilities is called the Bayes rule. And Bayes rule comes from two simple facts. So one simple fact is we know that the joint probability of x and y can be calculated using the product of the marginal and conditional. So it's a probability of x given y times the probability of y. And also there is a symmetry, right? Probability of x and y is the same as probability of y and x. The joint probabilities are asymmetric. And it's just the probability of y given x times the probability of x. So now those two are equal to each other. And from this equality, so let's write it down: probability of x given y times the probability of y equals to the probability of y given x times the probability of x. And now if we take and divide both sides by probability of y, then on the right hand side we just will have probability of x given y. And on the right hand side we're going to have probability of y given x times the probability of x divided by probability of y. So again, this is just a simple rule of probability, but when it's written in this form, we call this specific relationship Bayes rule. Bayes rule. Okay. Thomas Bayes was a reverend. He lived in England in 18th century, and he essentially used probability to update his knowledge about certain facts once he learned another related fact. And he demonstrated or visualized this type of process of updating probabilities using this imaginary game. So you sit on a chair, and there is a table behind, and there is a white ball on this table, and you don't know the location of the white ball. And what you do, you basically throw a black ball on the table, and then you ask your assistant related to the black ball where the white ball is. Okay, and assistant, for example, say it's upright from the black ball. And then you throw again another black ball, and your assistant says again where is the position of the white ball in relationship to the black ball. So imagine such a sequence. So your assistant always say upright, 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 upright. So you throw it at 10 times, and every single time your assistant says it's upright from the black ball. So then you basically can be pretty sure that the white ball is somewhere in the upright corner of the table, just because it's unlikely that 10 times in a row, when a black ball was thrown randomly, the white ball will end up being on the upper right from this black ball. So again, that's how Thomas Bayes designed this thought experiment, and he used this, which we nowadays call the Bayes rule, to calculate the probabilities of location of this white ball, and so thus the name. Okay, and usually when we apply the Bayes rule, you will be given the quantities on the right hand side. So you will know this conditional probability, you will know this marginal and this marginal, and you will have to calculate the conditional probability on the left hand side. And what you see here in this equation, it's the same equation, just the marginal is written in a slightly different form, because you remember the marginal can be calculated from a joint by just summing across the variable that you try to sum out. Okay.